Hello, good morning again. So in the last class, we have seen memory allocation. We started with the memory management chapter, and we have seen up to contiguous memory allocation. As you know, so memory allocation can be divided into two categories. One is contiguous allocation, and the second one is non-contiguous allocation. Right? Again, contiguous allocation, we have got two types. One is MFT and MBT. MFT is multi-programming with fixed number of tasks, wherein the partitions are fixed. Partitions are fixed in the sense their partitions need not be of the same size. Partitions, they are fixed partitions. They may be of different sizes, and one partition is assigned to each process. And as we have seen, so this multi-programming with fixed number of tasks, so it is able to run only the number of processes that we can run is equal to the number of partitions that we have. That is why it is called as multi-programming with fixed number of partitions. And the disadvantage, as you have seen, it suffers from internal fragmentation, right? Because whatever is the partition, suppose a process wants 250 kilobytes of memory, and we are assigning a partition of 300 kilobytes, and remaining 50 kilobytes wastage within the partition, so that is internal fragmentation, right? So this MFT suffers from internal fragmentation, right? And so that can be a little bit overcome by MVT. MVT in the sense variable partitions, right? A variable number of tasks. So the whole of the memory, the user space, it is as and when the process is on demand, right? So whatever the memory that is required by the process, we just keep on allocating, right? We just keep on allocating, and as and when the process completes its execution, so those partitions are created. So sometimes you can have 10 processes, sometimes you can have 15 processes, depending on the sizes of the processes, right? So that is why, so in MVT we can run variable number of processes, right? That is why it's called as MVT, multi-programming with variable number of tasks. And we have also solved one problem based on that, right? And we have determined, so there are basically three techniques for allocation of contiguous memory in case of multi-programming with variable number of tasks. So that is first fit. Okay, so first fit is the sense whatever the size of the memory the process creates, so we have got different partitions. So the first partition which can accommodate that process, so we allocate it, right? So that is first fit algorithm, first fit technique. Then best fit in the sense, the second algorithm is best fit algorithm. So whatever is the size that is required by the process, the smallest partition that can accommodate this process, so that is best fit. Then worst fit is the largest partition, the biggest partition that can accommodate the given process, so that is called as MBIT, that is called as worst fit algorithm. And we also solved a problem based on that, and we have determined, so what is the fragmentation, because MBT suffers from external fragmentation. There is no question of having internal fragmentation here in the sense, because whatever is the requirement of the process, only that much of memory is allocated, right? So there is no question of allocating excess memory so that there is internal fragmentation. No. Okay, so there is no internal fragmentation in case of MVT, right? So, and then the next topic that we have to see here is non-contiguous allocation, right? So the overall problem of contiguous allocation is it suffers from internal fragmentation. It suffers from fragmentation problem, right? So because whatever the memory that is required by the process, so much of memory should be contiguously available, right? Contiguously available. So that is the basic requirement of contiguous allocation. So due to this, it leads to what you can say the external fragmentation. It requires it suffers from external fragmentation, right? So this problem of external fragmentation in case of contiguous memory allocation, so we can overcome it by using paging. Paging, that is non-contiguous. There are basically two techniques of achieving non-contiguous memory allocation. One is paging, the second one is segmentation. First we will see paging. right? So paging is a technique wherein what we do. So before knowing what actually is paging, we need to know what is logical address space and what is physical address space, right? Right. So logical address space, it is also called as virtual address space. It is the, what you can say, it is the programmer's view of memory. It is programmer's view of memory, right? Because programmer doesn't have any idea of where his program will be stored in the main memory, right? So he assumes that his program starts at memory location 000 and he codes his program, he writes his program, right? Okay, so the user's view of the program, it is called as logical address, and whenever CPU starts executing the program, what it generates is, it generates addresses with respect to the user's program, right? Okay, so the addresses that are generated by the CPU while executing the program, so they are called as logical addresses. They are called as logical addresses, right? Again, it all depends on, so because normally we go for dynamic addressing, which we have seen in the very first video, right? So if you are using static binding, static address binding, right? So then logical address is same as physical address, right? So if we are using dynamic binding, then there is a need for conversion of every logical address into physical address. So normally we use dynamic addressing. That is why, so whatever the address that is generated by the CPU, it is a logical address, right? It is a logical address. Okay, set of logical addresses forms a logical address space, and this logical address, whatever that is generated by the CPU, it has to be mapped to the corresponding physical address by using what is called as a memory management unit, right? Memory management unit. So this memory management unit, it may be software, it may be a hardware, or it is a combined thing, maybe hardware, software embedded into hardware, something like that, right? Okay, so that is what is logical address space, right? So logical address space is, it is the whatever the addresses that are generated by the CPU, they are logical addresses with respect to, okay, it is, so what you can say is, so suppose this is, assume that this is the logical address space, right? So the whatever the memory that is, so that is required by the program, right? That is required by the program, user program, so that is logical address, you can say, right? So once CPU takes your program for execution, it keeps on generating the logical addresses. So every logical address has to be converted into physical address by using memory management unit. You will see that, right? So then physical address space, as you know, it is the primary memory. It is the primary memory, right? So the primary memory, it contains addresses in the lower part of the memory starting from 0000. So you have operating system stored. Rest of the memory is meant for the user, right? So every address that is generated by the CPU, it has to be converted into corresponding physical address, right? Okay, now assume that, okay, next we'll move to paging, right? So, so here in case of paging, what actually we do is, the logical address space is divided into, it is divided into pages. It is divided into pages, right? Pages of fixed size, right? Every page is of fixed size. As you can see here, I have divided this logical address space into 4 pages. I have divided this, the logical address of this particular process, right? Every process has a logical address space, right? So this, the logical address that is meant for this process, it is divided into 4 pages. It is divided into 4 pages, right? Now, if you think, right? So now, since there are 4 pages, right? So how many address bits are required to access a page here? Because there are 4 pages, that means you require 2 bits. You require 2 bits to access a page. 2 bits to access a page, right? Assuming that each page is of size 1024 bytes. Okay, 1024 bytes, right? Now, to address any location within the page, okay, so you have to access one byte within 1024 bytes, right? So, to access any location within 1024 bytes, so you require 10 bits because 2 raised to 10 is 1024 and 2 raised to 2 is 4, okay? So, to access any of the page, you require 2 bits. To access any location within the page, which is of size 1024, you require 10 bits, right? So your logical address, it will be of size 2 plus 10, so it is 12 bits. It is 12 bits, right? Okay, is that clear? Okay, next. So this is about, in general, you can say if the page is of size, if the number of, suppose if you have k bits reserved for page number and n bits reserved for the offset, okay, n bits reserved for the offset. So the total number of bits in the logical address space it is, so k plus n, you can say that, right? Okay, so this is what it is. So every logical address. So now moving on to this physical address. Moving on to this physical address, right? Moving on to this physical address. Assume that here there are, we use the physical address again. It is because again the physical address space is divided into fixed size frames. It is divided into fixed size frames, right? So there may be any number of frames here, and the frame size is same as that of the page size, because we are going to fit the page from the logical address space into the frame in the physical address space. Okay, so the size of the page and the size of the frame, it must be one and the same, right? So here the physical address is divided into number of fixed size frames. Okay, now assume that there are 8 frames, and of course the size of each frame is 1024, right? Then how many bits are required to address a frame? Okay, because there are 8 frames, so to address a frame you require 3 bits, because 2 raised to 3 is 8, so you require 3 bits to address a frame. And to address any location within the frame, because the frame size is again 1024, that's equal to the page size. Okay, so to address any location within the page, so you require again 10 bits. So your physical, the number of bits in the physical address, so that is equal to 13 bits, right? Okay, in this example, as we have seen, so there are 12 bits in the logical address space and there are 13 bits in the physical address space. Is that clear? Okay, so why there are 12 bits? Because 2 bits are required to address a page and 10 bits are required to address a location within the page. Similarly here, 3, because there are 8 pages, you require 8 frames, you require 3 bits to address any frame and 10 bits are required to address any location within the frame, right? Okay, ultimately in this example, so every logical address of 12 bits should be mapped to 13 bits of physical address, right? Okay, so now moving on to this mapping, address mapping, that means how every page is mapped to a frame, right? So as you see here, right? So this, what actually is the content of memory management unit? Okay, we'll see in case of paging. In case of simple paging, so memory management unit is nothing but your page table. Okay, memory management unit is nothing but your page table. So what actually the page table contains? This is the page table, right? So this is the page table. Okay, now assume that CPU generates a logical address. So this is the logical address, right? So n bit of logical address. So this logical address, it is divided into 2 parts, right? It is divided into 2 parts. First part is P, second part is D. First part is P, second part is D, right? So this first part P, it is used as index. It is used as index to the page table, right? It is used as index to the page table. Suppose we have 2 bits here, so it can be 0 0 means first location, 0 1 means second location, 0 1 0 means third location, 1 1 means fourth location, right? So it is used to address the page table. It is used to address the page table, right? So depending on whatever is the content of P, suppose it is 0 0 or 0 1, suppose it is 0 1, that means this location. Suppose it is this location. No? So whatever is, see here we have stored corresponding frame number. Okay. So here we have stored corresponding frame number. Let us say it is F, right? So F. Okay. So this frame number along with this D, D is nothing but it is offset, right? It is offset, right? So this logical address which is divided to P and D, this P is used as index to the page table. Okay, using this index, so we look into the location. So here we have stored some value for this frame number, right? So this frame number along with the offset, okay? So that is nothing but your physical address, that is physical address. So this physical address is used to address a location within the physical memory, right? So here also this F, okay, F is used to address the frame number, and D is used to address the location within the given frame, right? So wherever, so depending on the value of F, depending on the volume, suppose it is because assume that there are 8 frames. So suppose it is 110, right? 110 means, so it is 6th. So 0, 1, 2, 3, 4, 5, 6, right? So it is 6th frame. Okay, 6th frame, and depending on the value of offset, whatever is the offset value, so that whatever is the value of D, right? So in the 6th frame, okay, we look into the Dth location within that particular frame, right? Okay, so so assume that if there are m bits in the physical memory, so out of which so f bits are used to address the frame number, and remaining d bits are used to address a frame. Okay, so m is equal to f plus d, so that is for physical address, whereas n is equal to, so the number of bits in the physical address, so n is equal to it is the p plus d, n is equal to p plus d, that is physical address. So it indicates the page number, whereas here f indicates the frame number. So this is how the mapping takes place, right? So I will just repeat it once again, right? So whatever is the logical address that is generated by the CPU, it is divided into 2 parts, page number and D, that is offset, right? So this P, page number, is used as index to the page table. So page table contains, it is a mapping, it contains mapping information. So which page? So these are page numbers 0, 1, 2, 3, 4, right? So which page, each page, where actually to which frame they are mapped, right? So to which frame they are mapped. So it may contain 1, 5, 6, 7, right? It means that 0th page is stored in first frame. So first page is stored in 5th frame, like that, right? Okay, so depending on the value of P, so we access a particular page number, and we have got a frame number here. So that frame number is taken, so it is appended with D, that is the offset. So this FD, it is nothing but your physical address, right? Okay, so I will pause this video now.